All right, hello friends. It is time to talk about graphs, though we did talk about them a little bit in the earlier slides on relations. But now it's time to go get full-blown into graph theory. Okay, so let us begin with a funny example that I remember from this summer. Do you guys remember on Instagram some people were like sending out messages saying like, hey, do you want to be a part of a book exchange? And this was like the text that they would put in their stories. Well, that is in fact a pyramid scheme, and we can show it a bit, we can model it using graphs, using directed graphs, right? So you were supposed to like send a book to this person, and then also the person who they got this from, which is weird to think about, and then you kind of like pass it along. So here is the person whose message it was. And here is the person who they got the idea from. They are connected like this, or actually, how about this way? So like here's the poster, and they are required to give a book to this person who posted the message. And then if you decide to get in on this scheme, you also have to then give one book to this person, and also all the people that you give this message to, if you choose to share it, they all have to give you books, and also the person who posted. Okay, that is how the pyramid scheme works. And so there's a bunch of these little arrows going between people for, hey, this person is required under the pyramid scheme to give this other person a book. And so I think you can imagine how many arrows are going into people way over here. Okay? Tons and tons of arrows, assuming that this worked properly. Okay? Assuming that everybody like remembered to put their previous person there. Okay? So yeah, it just depends on how many people you share this with. Everybody before you also got a book. That is the idea. And so it's a pyramid scheme because eventually there's going to be one person over here who hasn't taken part in the scheme yet, and they won't find anybody to give them books. Okay? Like there's nobody over here to do this with. And that is the sad story at the end of the day, because if they participate, they have to give these people books. It's all horrible. Okay? So you can model relationships like these with a directed graph, like who got a book from who. Okay, that's all. So a fun little example, and that is one way to do things. Now it's time to go further. Let us talk about graphs that don't have arrows, that just have little lines between things. Okay, just to indicate that there's a relationship between these two vertices that doesn't really go in any particular direction, or maybe it goes in both. Okay, that's the idea. So this is called an undirected edge on these undirected graphs. Okay, so here's an example of an undirected graph, and you can essentially travel either way. If you want to go from A to B or from B to A, it doesn't matter. Okay, it's like you have two arrows almost. Okay, but there's no concept of that. So again, or maybe formally for once, a graph is two things, right? It's two things. It's a set of vertices. So V here is A, B, C, D, and E. And then it's a set of edges. And now the edges don't have to be like ordered pairs. They can be little sets of like A, B. There's an edge between A and B, like that. There's an edge between B and C, etc. And the direction doesn't matter, so that's why we use sets, because the order doesn't matter. Isn't that cool? So you got your vertices, you got your edges, and there's also a concept of a weighted graph. Okay, so maybe if you remember my example of a directed graph with like cities in between, and like this was a map, then the weight might be like the distance between these little cities. Okay, so yeah, you can weight a graph by adding weights to each edge. And so there's like a cost to travel between here to here, or here to here. Okay, that's the idea. So let's make up some weights. Like this could be 5, this can be -17, this can be 42, 12, another 5, and I don't know, 8. So you can make up weights for each of these edges. So like this one costs 42 to travel. So if I want to go from here to here to here along this path, it's going to be 25 total cost. Okay, that's the idea. Hopefully that makes sense. So yeah, that's graphs. It's a nice little high-level concept that you can use to model things with, like pyramid schemes. Okay, so let's talk about how graphs can get weird. So one way to do it is with parallel edges, which we really didn't talk about when we talked about directed edges. It was like, okay, if there's an edge from here to here, there's not like another. That wouldn't make much sense. But that's possible. It's possible in the directed graphs and in the undirected graphs. Like here are two parallel edges that potentially have different costs if you were to weight them. Okay, so those are parallel edges. They're multiple edges between the same pair of vertices. Who knows why you'd want that, but you can. Okay, so like maybe like the two endpoints, the two vertices are cities, and one's like a toll road that costs $5, and one's like a free highway that you can travel between. Okay, so there's two different ways to get there, and you can model that with a parallel edge. Okay, and then there's also the concept of self-loops, which was very, very important in relations, modeling those as directed graphs. You can also have a self-loop in an undirected graph, and admittedly it looks a lot weirder because there's no arrow going on. It's just like a circle. So you can have a self-loop between C and itself here still. Okay, and yeah, most of the time though, we care about graphs that look more like this, that look kind of normal, that are, we call them simple. Okay, simple graphs. They don't have parallel edges or self-loops. Okay, so we kind of get rid of that, and we get rid of that, and that's it's a simple graph. Okay, so this is a non-simple graph. Okay, so let us talk about the normal looking graphs now some more. We have a bunch of concepts to talk about, like from getting from here to here in different ways, right? So let's talk about these things. So the first term is adjacency. So if there is an edge between two vertices, we call those vertices adjacent. So like A and B in this graph are adjacent. They're right next to each other, right? That's essentially what adjacent means in Latin. And B and E, for the same reasons, they're adjacent. There's an edge connecting them, okay? So they're adjacent. A and D are not adjacent. You can get there, but not directly. Okay, so remember that. Then, here we go. Similarly to adjacency, we say that edges are neighbors of each other. Okay, so vertex C is a neighbor of vertex B because there's an edge that connects them. There's like, that's the lawn between the houses, yeah? So those are neighbors, and so that's like talking about vertices again. So who are all the neighbors of B? Well, we got A, we've got E, and we've got C. See that? And similarly, we could say that, okay, B and E are adjacent, B and A are adjacent, B and C are adjacent. You can kind of use both of those words to get to the same point, but it's sometimes quicker to use one word compared to another. Okay, then we also have degree. Okay, so degree is the number of neighbors. So like B, it had 3 neighbors, which means that its degree is 3. See that? Not bad. So yeah, that is quite nice. And sometimes we take these words and we apply them to graphs themselves. Okay, so we can say like there is a concept of having a degree for the entire graph, and that is the sum of the degrees of all the vertices. So the degree of the graph is, well, 2, because A's got 2, plus the 3 for B, plus C's got 3, plus D's got 2, plus E's got 2 neighbors. Okay, so 2, 4, 6 plus 6 is 12. So this entire graph has degree 12, we say. Okay, and that's just like a little way of, in one number, explaining like how complicated a graph looks, kind of. Okay, so that is degrees for both vertices and for graphs. And then one other nice thing that we can do is create a subgraph. And I think I've got way too much going on this slide, so let's make a new one to talk about subgraphs. I will copy what we had. So here's our nice graph. Let's make a subgraph out of this by picking just subsets of the vertices. So a subgraph, H is a subgraph of G when these vertices sets are, like this one's a subset. This one's a subset of the edge set of the original graph. That's all. So you can copy the same graph. And it's like, okay, yeah, this is a subgraph of the original one because it's subset with equality. So everybody's a subgraph of themselves. But you can also have like proper subgraphs, right? So here, let's pick out this edge and this edge and this edge, and that can be a graph, okay? Or maybe just to make it connected, that's another word, we can use that one as well. So here's a subgraph of the original one. I'm going to pick out the, actually I can pick out a different number of vertices too. So let's like get rid of E as well. So let's say it was what I was intending, B, A, C, and D. So this is a subgraph because the vertices are a subset of the vertices here, and the edges are also a subset of the edges here. See that? So a subgraph. Okay, so yeah, I've colored in a subgraph down here. That's all. Okay, we have changed it. So example of subgraph on the next slide. How about that? Okay, so we've got your weird graphs, we got your normal graphs. How about fancy graphs? Okay, things that people like to give names to for one reason or another. So let's talk about it. So a regular graph is nice because all the degrees are the same. So it's regular in that sense. That here's an example of a 3 regular graph where every vertex has 3 edges coming out of it, has 3 neighbors, has the degree 3, right? All of them do. 1, 2, 3. 1, 2, 3. So it's like pleasing to the eye, right? It's regular. It's cool. So that's a regular graph that you might hear again in like a question somewhere. Probably the most popular one that you're going to see in the literature when you go on to future classes is going to be complete graphs, okay? Those are important to think about a lot. So K is like probably German for the word complete, like we make the hard C sound anyway, so just think K for complete for this one, and that is the idea. So it's called the complete graph on n vertices, and it's sometimes also called a clique. We say clique in like real life when we're talking about like a clique of people who hang out with each other, but in math we call it a clique instead. So we pronounce the I differently for some weird reason. So maybe actually the K comes from clique. So this is K6, and it is the complete graph on n vertices. It has every possible edge between everybody, okay? So I should, let's define it down here. Has every possible edge, and still making it a, where is it? A simple graph. Okay, so there's no self loops. But this, every vertex can get to every other vertex. It is a clique. They all talk to each other. They can all connect. Okay? Is the complete graph on n vertices, k to the n. Okay? And then another weird one that's very important for an algorithms class that you will take eventually is k of n comma n. Okay? This one is an odd one. Okay? So it's like complete in the sense that there's a partition between 2 different sets of vertices. So let's just talk about the rules. All right, so it has n plus n vertices. So this is k3, 4. It has 3 vertices over here and 4 vertices over here, and it's complete in the sense that they're all right next to each other. Oops, sorry, I dropped my pen. Yeah, still works. So these two sets are like different, right? So these within the set, they don't talk to each other, but they go to everybody else outside. You see that? So everybody over here can get to everyone. There is an edge from this one to all of these. There is an edge from this one to all of these. From this one to all of these. And if you want to think about it in a mirror, that also works. This one has an edge to all of these as well, and so on and so forth. So that's like the complete graph with like partitions going on. Okay, so not as complete as this one, but still quite complete. There's a partition going on here. It's like a line being drawn. Okay, so that's KNM, and that brings us, keep this in mind, that brings us to our first question of the day. So take a second to figure out how many edges are in K34, and can you find like a pattern of this? And let's figure out if it is a regular graph as well. Okay, here we go. Here we go. So assuming you've tried it, let's go to K34. 3, 1, 2, 3, 4. How many edges? Did you figure out the pattern for that? Oh, we got 1, 2, 3, 4. One time, 1, 2, 3, 4. A second time, 1, 2, 3, 4. Third time, oh, that kind of multiplies, doesn't it? This is K34. So it has 3 times 4 equals 12 edges. So that's an easy way to remember. It's just this number times this number. And let's also figure out if it's a regular graph. What does that mean? So all the vertices have the same degree. Is that true? So let's see here. Dun, dun, dun. This one, let's look at this one first. It has 4. 1, 2, 3, 4. Its degree is 4. 4 neighbors. This one also has 4. Ooh, this might be working. How about this one? Oh yeah, still 4. Cool. All right, how about this one? Ah, that one has 3. So it's not the same. These ones, I guess if you could make a subgraph or do something weird like that, it's not a regular graph unless these two numbers are the same. You see that? It's like the 3 is saying how many things that, the degree of all the things on the right, and the 4 is giving the degree of all the things on the left, kind of, and they're not all the same, okay? So not all the vertices have the same degree, so it is not a regular graph, okay? So, fun stuff, right? All right, and graphs are beautiful. They're fun to draw, but we also like to use them in our programs to model things. So let's think about how to represent a graph inside of our computers. So they are just a data structure. They're another data structure that you don't usually learn in CSCI 41 because they're kind of weird, but that's okay. We're studying them now. So there are 2 main ways of storing a graph inside a computer. So here's our graph, and here's one way to represent that graph. So the first way, and probably the most common way that you will ever have to implement yourself, is the adjacency list representation. That makes things quite a bit easier because usually you don't have a lot of edges, okay? And so it saves space compared to this one that we'll talk about soon. So with an adjacency list, every node in the graph, every vertex gets a spot, okay? Every spot in like a hash table, okay? Or maybe just an array of all these different vertices. And so think of this as like a map, maybe. Map / hash table / unordered map. And it takes these vertex names to lists of all the places they go to, yeah? So this can work just as easily if this were a directed graph. You just give like A to, okay, which of the things does A go to? What are the edges coming out of A? So here's how you do it. You say that, okay, A goes to B and C. So coming out of A, we have B and C, a list containing B and C. See that? And okay, starting at B, where can we go to? What are the neighbors of B? Well, we have A, C, and E. And so in the map at B, we're going to give the list of all those other vertex names that we can get through from an edge, A, C, and E. So it's like, it's telling us that AB is an edge, AC is an edge, BA is an edge, BC is an edge, BE is an edge. That's the idea. That's what's going on. So it's like a map from vertex names to lists of vertex names. Okay, and so you could make a type def in C++ to just whenever you say adjacency graph, you really get this type. So that's what a type def gives you. It gives you another name for an existing type. So you could say something like, now you could say something like graph G, and you can start filling it. Okay, so this is like, it gets replaced with this entire type. That's what a type def does. It's cool. So that is one way to store a graph. The other way, the other common way, is using a matrix. Okay, a matrix must be n by n because you don't know ahead of time. You can't like make a non-square matrix for graphs, unfortunately. You have to store it like this and put a 1 or a 0 depending on whether or not there's an edge between these two things. Okay, so again, with a undirected graph, this is kind of duplicated across this axis, but with a directed graph, you kind of need both sides. Okay, so this is saying that, okay, there's an edge between 1 and 2. So look up 1, look up 2, yeah, there's an edge there. And similarly, look up 1, look up 2, yeah, there's an edge there. So you got to put it there twice for an undirected graph. And it's 0 when there's not something there. Okay, so there's no self loop at 2, so we're going to put a 0 here. So it's like true and false. That's all. Okay, so those are the two ways to store a graph. And I should say that the matrix representation is used less often because it wastes space. For what are known as sparse graphs. And this just means graphs where there aren't a lot of edges. And that's most graphs. Because very not often do you get a clique like this. Do you get a complete graph where you kind of like put a 1 in all the places. And so it makes no difference between using this and this. But this representation is so much better when there's not a whole lot of places that you can go from each vertex. Okay, that is the idea. Okay, so that is the two ways to represent a graph. And let us go now to another question. Okay, so here's a graph G. Let's call it G. If only I could write the letter G. And I want you to give the two different representations of this graph. Okay, so give an adjacency list based on this, then also give a matrix representation, and instead of like numbers here, you can give just be like A, B, C, D, and E. Okay, so please do that. This is good practice, and we'll come back and do it together. Okay, so let's do adjacency list over here. So we've got 5 vertices, A, B, C, D, and E. And those are all going to map to a list that tells us where we can go, what edges are there from A, from B, from C, from D, from E. Okay, so from A, we can go to B or C. And so we're going to put in the adjacency list B and C. Okay, so really this is a linked list. I know I'm drawing it like an array, but it's just easier to look at. All right, from B, because this is an undirected graph, we can also go from A and we can get to C. So we got A and C here. So there is a little bit of a duplication with an adjacency list undirected graph, but that's okay. That is fine with us. From C, we can go to A, B, E, and D. Ooh, C is connected. He knows. He's got a lot of contacts. All right, so from C, we can go to A, to B, to D, to E. Very nice. Good for you, C. Then D can go C and E. And E can go to C and D. Okay, so that is the adjacency list representation of this graph G. And this is all you need to know about what the graph looks like. You can draw the graph from this. You see that? It loses no information. It is a representation of the graph in just a different non-graphical form. Okay, now the matrix time. Let us do it. So we need A, B, C, D, and E, and hopefully I give myself enough room. A, B, C, D, and E. And then you fill them in. Like, is there something between there? I don't think there's any self-loops in this graph, so we can put a 0 on the diagonal, because there's E doesn't go to E. Now, we look here. We have to cover all our edges. So there's one from A to B, okay? So from A to B, we put a 1. And similarly, from A to B in the other direction, we also put a 1. We mirror this thing. All right, we covered that one. How about B to C? So BC would be here. There's a 1. And also BC here would be a 1. You mirror it. Okay, so I'll do the rest a bit faster now. So C to D, we've got C, we've got D, we've got a 1. We've got C, and we got D in the other direction, we got a 1. Okay, DE, 1, and then ED, 1, yeah. Then CE, 1, CE, 1, and then the rest are zeros. Okay, so the nice thing about adjacency lists is there's no concept of zeros. You just don't have something here if it's not there. With a matrix, you got to fill in every row, every column, every entry. So I don't feel like putting little dashes because I will probably mess up my lines. So that is your matrix. Okay, that is the idea. Maybe I can like draw some kind of separation here at least. There you go. That works. Okay, so we are getting good at graphs. Okay, see, it's really not too bad. It really isn't. There is a lot of new words to learn, but they are more or less self-explanatory. With enough practice, they're not too bad. Okay, so let's talk about moving around not just by an edge. We can go from here to, like, we can get from A to E in multiple ways actually, but we haven't talked about like what it means to do that yet. Like what's the word for that? So let us do that. So I guess the first term is a walk. That's kind of like the most general thing you can do in a graph. You can walk to places, and a walk can go between different vertices and along edges. So a walk from some starting vertex to some ending vertex in an undirected graph is just a sequence alternating vertices and edges, because you're like, okay, I am here starting at this vertex. I'm going to get to V1 by following this particular edge. Because remember, this is the most general thing, you could have parallel edges. It's totally fine. So we got to say which edge we're following as well in a walk. Okay? That is very important. So we're getting to V1 from V0 by following this particular edge. We're getting from V1 to V2 by following this particular edge. We're getting to from VK minus 1 to VK by following this particular edge. And VK can totally probably be V0. Okay? That totally works. There's another name for that though. Okay? So this is a walk. This is the most general term. So a lot of the time you don't need to specify the edges because you have a simple graph, you don't have parallel edges. So it's like, okay, yeah, I'm getting here to here to here. There's only one way I could possibly gone following with these vertices in between, okay? Because there weren't parallel edges. Okay, so that's quite nice. And that leads us to the length of a walk. So here's my walk, ACE. That is length 2, not length 3, because there's only 2 edges to follow, okay? So that's the length of a walk. It's the number of edges. In this example up here, it's going to be k, yeah? Even though it's got k plus 1 vertices in between. See that? So it's very easy to get an off by 1 error here. All right, how about a closed walk? So that is where the first and the last vertices are the same. So it's like you make a little loop. So for example, here is a closed walk. You can go from A to B to C back to A. Okay, so that's a closed walk. It has length. How many edges? 1, 2, 3. See that? And it has, it's going to go between the same number of vertices, but it's going to hit A twice, once starting, once ending. So that's a closed walk, and then an open walk is where they're different. So like this one that I gave originally, that's an open walk. Okay, where the ending vertices are not the same as the starting vertices. Okay, So that's a closed walk and an open walk. How about a circuit? Okay, so a circuit is a special kind of closed walk where you're making a loop. Actually, my example was more technically called a circuit because here's what you can do. You can traverse the same place in a walk. Okay, walks, that's okay. You can go from C to D to E and do it again. Okay, that's still a walk. You're covering 6 edges in that case. Yeah, but if you don't want to retrace your steps, you can use the concept of a circuit. It's a closed walk where you don't overlap. Okay, no edge occurs more than once. Hopefully that makes some sense. So this was a circuit, but if I want to do something like this, that is definitely not. Okay, can't double up on the same edge. And yeah, that is the idea. And oops, I'm sorry, I wrote this down wrong. A path now is going to be a walk where no vertex or edge occurs more than once. Okay, so loops don't count, that's not a path, because the vertex appears twice. But this is a path. This original one that I gave, that's just a path. Okay, it's a place that you can go to and you're not doubling up on any vertices or edges. All right, and then finally, we have cycles. So a cycle is a circuit. It's a circuit which remember, it's a closed walk where no edge occurs more than once, and it's a circuit of at least length 1 in which no vertex except for the first and last occurs more than once. So let's see here. Let me show you a circuit, but not a cycle. Okay, here is a circuit. Bam, bam. I think that's going to work. Bam, bam, bam. That was a circuit, okay? Because I didn't reuse any of the edges. But that is not a cycle because I got back to C in the middle there. You see that? Because I reused the vertex. So circuits are about edges. Cycles are about vertices, okay? That's the idea. Though the first and last vertices are, of course, going to be the same in a cycle. So that's the difference between a cycle and a circuit. I hope that makes sense. All right, so I am sorry. There are a lot of words you need to learn when you're learning about graphs, unfortunately. But after I've thrown them all at you, I guess there's not a problem. Okay? They will be stuck in our minds because I have many examples. So let's talk about connectivity. I have thrown that word around a little bit, and I want to fully define it now for you. Okay, so we say that 2 vertices, they are connected in the graph if there is a path between them, which is nice. That makes sense. A is connected to D, even though there's not an edge between them like this, even though we don't have this, but I can get there. I can get there with a path. Okay, that's the idea. So that's quite nice. 2 vertices are connected if this happens. We can also say a set of vertices is connected if every one of them, every pair of those vertices is connected. So for example, this entire set of vertices, like A, I, H, D, and F, is connected. Because there's a path between everybody and everybody else. So if H wants to get to I, it can use an edge. If D wants to get to I, it can use a few edges. It has options as well. It can either go that way or that way, right? So that's quite nice. These are connected, yeah? This is also connected. All these are connected. B is only connected, sadly, with itself. It's sitting there alone. So that is the idea. You can also talk about the connectivity of a graph at once. So a whole graph is connected if the entire vertex set V is connected. Otherwise, it's disconnected. So this whole graph, let's call it G, or darn, it's already here. So like, I don't know. Let's call it blue G, who cares? This entire graph here is disconnected. As a whole, it's disconnected. Because they're little islands. We can't get from F to C, we can't get from D to B, things like that. Okay, so there's like a partitioning going on here in a sense. Yeah. So that brings us to connected components. So these little partitions, those are connected components. This is a connected component. This is a connected component. This is a connected component. This set right here, like if we exclude this f right here, this is a connected set of vertices. That's fine, but it's not a connected component because we could have added f. Okay, it's a maximal thing. So a connected component, it's a maximal set of vertices that's connected. So it's not like this is a connected component. We have to bring in everybody that it's connected to. See that? So that's a connected component. So is this, and so is this. So there are 3 connected components in this graph. You see that? That is the idea. So that is our terminology for now. We had a lot. Okay, we went from moving around all the way to connectivity and like partitioning a graph into its connected components. That was a lot, I know. But now we're ready for a little bit of a break to have a question. Okay? And oops, sorry, one question was about a term that I didn't feel like giving you because it was just an extra one that nobody ever uses. Okay, so let's do these 4 and let's see if it's going to work. So go ahead and try them all and then we'll come and do them together. So here is an undirected graph. Let's find the maximum length of a path in this graph. Let's figure out what it could be. Okay, so remember what a path is again. It's a walk where no vertex or edge occurs more than once, so we can't like double up on anybody. I think we can visit every vertex though. How about that? What about this path? Can't get any longer than that, right? Because you can't double up on vertices. So that should do it, I think, right? That is a path where I am not having any vertex or edge occur more than once. So there is a nice path for us. That can be A. Let me move this away because I'm going to have to draw many things. This is A. Okay, hopefully you can see that. That was A. Then, okay, how about B? What's the maximum length of a cycle in the graph? So the issue is we can't use everybody. We can't give every vertex a part in the cycle because C will not work. We can't like go and come back because we can't use the same edge in a cycle. Yeah. So we're unable to add C to any particular cycle that we have because there's no way to get out of C a different way. Hopefully that makes sense. But the biggest cycle then would therefore be these guys. All the other vertices. See that? So that's a nice cycle. And remember that a cycle it's just a circuit of at least length 1, and we're not doubling up on any vertices. Okay? So that is B. All right, C. What is a closed walk of length 4 that is not a circuit? So that's quite a lot of things that we want here. So a walk where the first and last vertices are the same. Okay. So we need a walk that ends in the same spot, and we need it to have length 4. Okay, but it can't be a circuit. And what's the difference? A circuit, where no edge occurs more than once. So we have to double up on the edges. Okay, so that will be a nice closed walk of length 4 where we have like reused things. So I think, let's see, we've got to end in the same spot. It's got to be of length 4. So here's my idea. Let's go here, here, and then back. Here, here. So we double up on 2 edges, and it's length 4. And because we double up on edges, we unfortunately do not obtain a circuit, but it was a closed walk. Okay. And then finally D, give an example of a circuit of length 0 in the graph. Okay, let us find that. A circuit is a closed walk in which no edge occurs more than once. Well, let us not use any edges at all. Let's just start at D and stay at D. That is a circuit of length 0. Okay, that's the idea. So just stay in one spot. That is our answer to D. Okay, hopefully that was all not too bad. Hopefully you got these. Sorry for the way I have to draw the answers. Hopefully you can read the graph from that. All right, coming up next is a fun little piece of information about two famous people who invented these, Hamilton and Euler. So different kinds of ways to get around in a graph in a fancy way. Okay, so here is, let's talk about Hamiltonian cycles and paths, and then also Euler for a little bit. Okay, so a Hamiltonian cycle in an undirected graph, it's when you have a cycle and it includes every possible vertex in the graph. Okay, it's special like that. So every possible vertex. Okay, that is the idea. So here we go. I am going to find you a Hamiltonian cycle that includes every vertex in this graph. So we've got 1, 2, 3, 4, 5, 6. Yeah, there we go. That is my little Hamiltonian cycle for you. There it goes. And then a Hamiltonian path, it is a path that includes every vertex, and you can just, well, find a Hamiltonian cycle and then drop the last thing. So like bam, 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 bam. That works as well. So you don't have to come back to where you were. It just has to find every possible vertex. It doesn't have to be part of a Hamiltonian cycle, but sometimes that's an easy way to find one. Okay, so if you find a Hamiltonian cycle first, it's very easy to find a Hamiltonian path as well. You can just like take out one of the vertices. But it doesn't have to look like that. It doesn't have to end in a cycle. Okay, so that's Hamiltonian stuff. Now let's talk about Euler stuff. So an Euler circuit is when you visit, it's like a bit more powerful than a Hamiltonian cycle, so it's harder to get. It is it's when you have a circuit in an undirected graph that includes every vertex and every edge. Okay, so it's a bit more powerful. And I have a story for you now. So back in the day, they put, I don't know if they still do this, but in my elementary school, on the backs of milk cartons, they put little little brain teasers. And so one day in second grade, pretty sure it was second grade, I honestly don't remember, first or second grade, they put this picture. Obviously they didn't label it or call it a graph. They put this picture that kind of looks like a house on the back of the milk carton, and they said, can you draw lines from every circle to each other such that you fill in the entire thing? Okay? And really, what they were asking for was for you to find an Euler circuit in this graph. Isn't that cool? So I honestly don't know if I remember how to do it, but I will at least give it a try, and if I can't find it fast enough, I will just pause the video so that you can all see me do it later. And I think that was it. I'm pretty sure I just did it. Yeah. So every vertex and every edge, that is an Euler circuit in this graph. And that is just me living my second grade dream of solving that puzzle. It bothered me for weeks. Okay, so that is Hamiltonian cycles and paths, and now it's your turn. So go ahead and find a Hamiltonian cycle in the following graph. And so you just have to find like a nice way to go through every possible vertex. Okay, so find a nice Hamiltonian cycle in this graph, and remember that you got to wrap back around to where you started. Okay, well, let's see what we got here. So we got to cover everybody, and we have to somehow end up where we started. So let's go like this, like that, like that, like that. This might get us into trouble. I'm not sure. That, and yeah, we can come back here. Cool. So that is one example of a Hamiltonian cycle. Obviously, there are many more, but that is one. So hopefully this is all not too bad. It's just weird terminology, I know. That is the idea. So you've learned a ton about graphs today. You're going to read more about it in your book, and hopefully that'll also make it all come to you a bit more. So the last slide that I want to give you today for this lecture is called Traveling Salesman. You'll also hear it be called Traveling Salesperson, and maybe we should update this. Let's make it Traveling Salesperson. Doesn't matter your gender. You can sell things. Okay, so here's the idea. You are selling something, like you've got a little briefcase and you're going door to door, you're selling things, and you want to efficiently like sell your stock, okay? You want to, and by efficiently, I mean you're traveling around city to city, like living out of your other briefcase that you're not using to sell stuff out of. And so you want to be very frugal, and you want to travel the shortest amount of distance between all of the cities that are on your list of places that you need to go to. So you need to go to all of these cities and sell things. You need to find a circuit, a cycle in this graph that minimizes your total distance traveled. Okay, so that is the traveling salesperson problem. You have a list of cities and the distances between each of them. So you can go from here to any of these other ones, but it would behoove you to go to the best one, okay? So you want the shortest possible route that visits every city exactly once and returns to where you started, okay? So this is surprisingly a very hard problem. So here's the idea. You can totally model this as a weighted graph or an undirected weighted graph, and you can try all the permutations, like, okay, I'm going to start here, and I'm going to try all the different ways out of 2. I'm going to try all the different ways out of 1. I'm going to try all the different ways out of 4, and trying to get to everybody. That will eventually find the shortest path, yes, but that will take all the permutations worth of time, so like n factorial time, though, which is unfortunate. So that is the idea. Here's a fun one, though. This is the traveling salesperson problem solution for visiting all the state capitals. So here's all the capitals for every state, and here is the shortest way you can get through all of them. Okay, so if you're ever planning on doing this, this is the route that you should be following as close as possible on the real roads. Okay, because that will save you on gas. That is the idea. Okay, so let me just say now, this is like intro to algorithms. This is a ridiculously hard problem, the traveling salesperson problem. It is very, very hard to do, okay? We haven't really come up with very good algorithms that are much better than n factorial, okay? That's the idea. Our best algorithms are all exponential time, which, if you remember from our SAT solving lab, that is horrible, okay? That's a horrible amount of time. So it took quite a while for them to figure out this solution, let me tell you. That is the idea. And then if that fun p equals np, then maybe there's an easier way. But until then, we have no clue, okay? We have no clue if we can't do any better than exponential, okay? Which is a fun thing. So let's figure out the traveling salesperson problem for this one. We've got 10. That's probably a good one to use. 15. And then that kind of forces us to use 35, which may be the best, and I'm not really sure. What else do we have? I would spend too much time probably trying to save all of these things. It definitely doesn't make sense to, yeah, maybe we have to go from here to here maybe, but that's no fun. That's like that. Yeah, I have no clue what the solution is, but there is a solution, I promise. Okay, that is the idea. So that's where I want to leave us today. I have really not too many slides left for you in this set. Maybe we'll end early so that you can study some more for the midterm. That is what I have for you today. So we learned a lot about graphs, okay? And really, they're not too bad. Just a bunch of terminology, but hopefully you're seeing that it's not too scary, okay? So let us come back in the next lecture and finish up these slides, and I will see you then.